it's even more interesting, because having counted, or more properly enumerated, as assigned an integer index to all the possible inputs, can we enumerate all the possible Turing machines? Now, to do that, we need to, well, I suppose there's lots of ways you could imagine doing it, but one of the easiest ways is to try to come up with first a scheme for reducing or encoding Turing machines as binary integers. And at the heart of that, we know that the Turing machine has a set of states, a set of input symbols, a set of symbols that can be written from the tape, a delta function that describes how you make the transition from one state to another, and a set of states that are considered to be, or a state that's considered to be the initial state, a set of states that's considered to be the final state. Well, at the heart of all that is that delta function. And so we have this function delta. Oh, messed it up. Try again. There we go. So there's our delta. And we know that normally when we talk about delta, we say that what delta does is it tells us that if we are starting in a certain state q sub I, and we see a certain symbol on the tape, x sub j, that then the function gives us a triple, and one element of that is what state q sub k we're going to go into. The second element of that is what symbol x sub l we will write onto the tape. And finally, what direction d sub m we want to move that in. Looks much better. All right. So basically the delta function takes two things in. One of them a state, one of them a symbol, but we're used to numbering our states. We can certainly number our symbols as well. And so we can, we normally think of having been given a set of x sub I. The direction is a little bit stranger, but we just have to sort of say something like, well, d sub 1 is left, and d sub 2 is right. And just agree then that there are two possible d values that we can give our automaton. All right. So the delta function takes two inputs, gives us back a triple of outputs. But functions are really just tuples. So I can actually encode any particular transition by just telling you those 5 indices, I, J, K, L, and M. So if you tell me that I'm going from Q sub I to Q sub J to Q sub K when I see a J there, X sub J there, and that then I will write out X sub L and move in direction D sub M, I can just record that as a tuple of the 5 integers. As long as I know which state is which and which symbol is which, that works. All right, well, this is interesting because each of those is integers. And again, we know lots of ways to encode integers in binary strings. Now, if we try to do the obvious thing and encode them in ordinary 0-1 binary form, we'll run into a problem because here we're not just encoding individual integers, we're encoding a tuple of integers. And so we actually need to encode the separators between them, the commas, in other words, as well. But we can handle that. And the way we handle it is we say, look, what I'm going to do is I'm going to encode that I as I zeros, or 0 to the I. And then I'll encode the comma as a 1. And then I will encode that J as J zeros. And I will encode the K as K zeros. And I will encode the L as L zeros. And I will encode the M as M zeros. All of them separated from one another with ones. And so if I've actually got, let's say, delta sub Q1 X2 says go to Q2 X1 D1. All right, I would actually encode. Really? It's playing games with me now. I would actually encode that. All right, let it be a small delta. I don't care. I will actually encode that as a single 0 for the Q1, followed by a 1, then 2 zeros for symbol 2, followed by a 1, then 2 zeros for the Q2 on the output, followed by a 1, then 1 0 for the X1, followed by a 1, and then 1 0 for the D1. By the way, this may show why, or hint at least why, up above, for the first time, perhaps in your entire careers as computer science majors, you saw somebody in a computer science class start counting from 1 instead of starting counting from 0. Because this would get a little bit messier, potentially, if we had to cope with things like numbers of zeros in there. So we're going to, for the purposes of this discussion of enumerating Turing machines, we're always going to start counting everything at 1. Now, that's transition, and I can get lots of different transitions, that will all have this kind of form of basically being 5 groups of zeros separated by 1s. Now, what is the entire delta function? Well, it's just a whole collection of these very specific mappings that represent all the possible transitions that we want to make. So each of these numbers represents a transition. If I collect together all the transitions that describe the delta function for my Turing machine, I could, in fact, encode the entire delta function. And the way I will do that is very simply, I will say, well, I've got all these nice individual encodings. I will separate different transitions in the delta function with 2 1s, because my internal scheme for encoding a single transition never uses more than 1 1 at a time. So I can put together then as many transitions as you like, as long as I separate them with a pair of 1s. Now, here's the thing. If I know the transition function, what else do I need to know in order to recover that Turing machine? I mean, you and I might not like to actually try to recover a Turing machine, from this, but we can certainly envision a program or automaton that could do it. But what's missing from here? Well, not a whole lot. We don't really need to know, for example, ahead of time what the list of symbols is. We can actually just sort of look in the 2 symbol positions of our encodings, all right, which I guess would be here, for example, and probably there. We can look at those and see what the largest number of zeros is, and that would tell us how many symbols we've got to deal with in this Turing machine. Similarly, we don't really need to be told ahead of time how many states we've got, because we can just sort of look at the input and output state positions in all of our transitions and figure out how many total states this Turing machine appears to have. So we can get all that out of the delta function. About the only thing we can't get out of the delta function are which state is the initial state and which states are the accepting states. Okay, that has a real easy solution. We just say, guess what? Let's let Q1 be the initial state. And if you happen to write a Turing machine where Q12 is the initial state, just renumber them. And we'll let Q2 be the accepting state. Because Turing machines, we know, halt the moment they get to an accepting state anyway. So we don't actually need more than one. You know, if you've got 12 accepting states, just gather them all into one and point all the arcs at it, and that's enough. With that much information, this encoding of the delta function captures the entire Turing machine. All I needed to do was add those extra conventions. So that means that I can represent a Turing machine as a binary integer. And that does something very interesting because, yeah, some Turing machines will have more digits in them than others with this encoding. A Turing machine with only a few states and only a few transitions won't have that many, of these transitions for us to actually map in there. Other machines will have, hundreds or thousands or even more transitions making up their delta function. So these strings can be of highly different lengths, but they're still just made up of zeros and ones. And we just gave ourselves a way to enumerate all possible strings made up of zeros and ones. So now I can say that we've actually got a way to enumerate all possible Turing machines. We'll say let M sub I be the Turing machine whose encoding in that above scheme is Wi according to our list of possible strings of zeros and ones from earlier. And that means that now I can talk about what is Turing machine number 100. And, from that, I go back to this table and I figure out, all right, what is in line 100 of this table? Might take me a while to figure it out, but, again, that's what computers are for, right? I can certainly imagine figuring that out, and then that becomes the encoding for my Turing machine. I recover my delta function. Now, first thing to realize, most of the numbers that we will get in this listing will lead to very, very bad Turing machines. For example, with this encoding, we should never start with a 1. So all these strings that actually start with 1 right away, we know are not syntactically correct Turing machines. That's okay. If we have a string that does not give us a syntactically correct delta function, we'll simply say that corresponds to a Turing machine that halts immediately. Doesn't even consume a single input. Okay, we'll adopt that as our convention. So if it's not syntactically correct, it just halts immediately. That means that then every position in this long list of W sub I corresponds to a Turing machine. And every Turing machine that you can write using JFlap or whatever, once you draw out those states and work out what the transitions are from state to state, you can encode that as one of these integers. And the fact that it is an integer made up simply of zeros and ones means it will fall somewhere into this list. And so then that list, M sub I, the Turing machines whose encoding correspond to the WIs, is an enumeration of all possible Turing machines.